All right, I am back on the air tonight, and tonight you're going to work on some more systems dynamics. First, I'm going to finish where I left off earlier today, or rather in the last video. So, yes, that's what we're doing. Let me, there we go. All right. So, where we left off on this is we figured out the steady state command error. Now, for the next part, we're going to figure out the steady state disturbance error. And this isn't going to take long. So the steady state disturbance error, you just got to go back to we have to go back to this equation right here. So let me move the yellow to the side and grab this expression. I'm going to copy it. And right here, I'm going to make some more space. Here we go. I'm going to parse this out. So what I'm doing right here is we're recalling the expression that kind of gives us everything. It includes our input, and it also includes the input disturbance, and it includes the output of the system. But in this case, since we're considering only the disturbance, we're going to get rid of the input from the system. So this is gone, it goes away. So now this just becomes y of s equals minus capital Y of s multiplied by k sub p plus ki over s all over 5s plus 2 minus t sub d of s all over 5s plus 2. So now we can rearrange and get our new transfer function that describes the gain of the system, and the gain being the output over the input. So I'm going to bring that over. Okay. And then we're going to group these terms together. All right, now we can create our transfer function, which will look something like this. Y of s all over t sub d of s will equal -1 all over 5s plus 2, 1 plus k sub p plus k sub I all over s all over 5s plus 2. All right, there is that expression. So now you can see here that we can just, like before, we can simplify this. So let's go ahead and do that by multiplying the top and bottom of this fraction by 5s plus 2. This simplifies the numerator, and it simplifies the denominator too, mostly. So now we're going to have capital Y of s all over t sub d of s equal -1, 5s plus 2, plus kp plus k sub I over s. So now we have to multiply the top and bottom of this fraction by s. And that's just to put it in its proper form. So we'll do that. Multiply top and bottom by s. And then what we're left with, capital Y of s all over t sub d of s equal -s 5s squared plus 2s plus kp of s times s plus k sub I. All right, now we have that expression. And let me paint this yellow, indicate that it's kind of important. All right. So now what we're going to do is we're going to recall the error function. And the reason why we're recalling it is because we need it, because it's part of the final value theorem. So we can indicate our steady state disturbance error. All right. I'm just checking something real quick. So there we have it. So the error function, recalling it, is going to be y. Let's pull up real quick. Y sub r of s minus capital Y of s. We know that the input to the system is 0, since we're only considering the disturbance. So we're treating the disturbance like an input. That's 0. And now we're going to have E of s equal -y of s. Now we need our transfer function in the error function to make this work. So what we're going to do is we're going to go multiply this by 1. But that 1 will be T sub D of S times, all over T sub D of S. That's where we're multiplying this by, which will then yield negative H sub D of S. Because, again, we're looking at this trend here, right? These are the same thing. So, T sub D of S. This isn't that bad. It's, for the most part, kind of simplified for us. So, capital E of S will equal now negative S 5S squared all over 5S squared plus 2S plus KP of S plus KI, all multiplied by 1 over S. So that is our S equation. So now we're going to plug this into E as that approaches infinity for the disturbance. As the limit as S approaches infinity. Well, it's going to be S times 1 over S. And S 5S squared plus 2S plus KP of S plus KI. And if we plug in 0, and if you notice these S's, they kind of cancel out. But nonetheless, we plug in 0 for this. 0. 0. 0. We know 0 over 1 just equals 0. So for this portion of the problem, E as it approaches infinity is going to equal 0. And that is the answer to this problem. All right. So now we're going to have exercise 3. That's the one we're going to do now. So I'm going to jump to the PowerPoint, and I'm going to show you guys the exercise that we're about to do, and then I'm going to snip it and drop it in. So here's the exercise. Now I'm going to go ahead and snip it. So here's the problem, dropping it in. So hopefully you guys can read this. So doing what we've always done, we're going to start off with the givens / assumptions. / assumptions. I'm actually going to do this problem blindfolded, so that means I'm not going to have any notes. So the first thing we're going to do is we're going to start reading the problem. So it says, consider a proportional derivative control of the angular displacement, first order motor system, in the exercise number 1. Okay, we're considering that block diagram, but it's different. The dominant time constant is specified to be 2 seconds. So we're given a time constant of 2 seconds. Okay. And a damping ratio is specified to be 1. So we're given a zeta of 1. It's going to say, and it's asking us, defines, okay, 1, compute the required values for Kp and Kd. So part A, we're going to look for case P and case of D. And then it says to evaluate the steady state command error and steady state disturbance error, given that both the command displacement and the disturbance torques are unit step functions. We can do that too. So that's going to be B, steady state command error, and C, steady state disturbance error. All right. So the first thing that we're going to do is we're going to find the closed loop transfer function. So I'm actually going to grab a bigger picture, not much bigger, for that transfer function. So here's that picture. So the first thing we're going to do is we're just going to kind of break apart this and figure out its closed loop transfer function. So the first thing I'm going to do is I'm going to define the error function, which is going to be theta sub r of s minus theta of s. Pretty easy. We're going to define t of s, which is just going to give us e of s times kp plus e of s times k sub d of s. And now we know what this piece is here. I'm going to change the color for us. So this piece here is just going to be t of s minus t sub d of s, which is going to give us theta. Theta of s is equal to capital T of s minus t sub d of s all over well, it's going to be 10s squared plus 2s. Okay. I'm kind of going to separate this. And I'm going to do different colors, and I'm going to start back substituting these equations into each other. So the first thing I'm going to plug in is the E of S equation. So T of S is going to equal theta of S minus theta. And here we have Kp plus K sub d of S. There's that. And we can FOIL this out, and it might benefit us if we do FOIL it out. So if we do that, we'll have Kp theta sub R of S plus Kd of S, theta sub R of S Okay, then we'll have minus Kp theta of S, and then we'll have minus K sub d times S times theta of S. So we can group our like thetas together and simplify this a little bit. So actually, I need to pull this negative out. Which is going to give us Kp plus Kd of S. So there's that. So now I can plug in T of S into the theta of S equation. So theta of S is going to equal theta R of S Kp plus Kd sub d of S all over 10s squared plus 2s minus theta of S Kp plus Kd of S all over 10s squared plus 2s. And the last piece is going to be negative T sub d of S all over 10s squared plus 2s. So now, this is the full meal deal right here. This kind of has everything we can possibly want for later on in the problem. And I kind of like doing this because you do the hard work once, and then you can refer to this expression again and use it for other things. So this is nice. So now we're going to go ahead and find the we're going to find the transfer function for the command error H sub C of S, right? So in this case, when we're looking for that, the disturbance, we're neglecting the disturbance, and it's 0. So it's theta of S equals theta sub R of S Kp plus K sub d of S 10s squared plus 2s minus theta of S K sub p plus Kd times S all over 10s plus 2s. So I'm going to move 1 over to the other side. And it'll look something like theta S plus theta of S Kp plus K sub D S all over 10 plus 2S. Okay. Equal theta of R of S Kp plus K D of S all over 10S plus 2S. And going back here, I know that this theta of S just turns into 1 minus Kp plus K sub D of S all over 10S plus 2S. I know that will equal theta of R of S Kp plus K sub D of S all over 10S squared plus 2S. So now this becomes theta of S all over theta sub R of S equal Kp plus K sub D of S 10S squared plus 2S 1 minus Kp plus Kd of S of 10S plus 2S. So I'm going to do what I've done before. Multiply both top and bottom by, don't forget it's squared, 10S. Shit. Pardon the language. So it should be 10S squared plus 2S all over 10S squared plus 2S. And we see that these guys cancel out mostly, because you know that 1 does get multiplied by the 10S squared plus 2S. We know that. So the theta of S, theta R of S is going to equal Kp plus Kd of S. Kp. So it's just going to be 10S squared plus 2S minus Kp plus Kp plus K sub D of S. Let me double check this real quick. Rather be safe than sorry, right? Yeah, that's right. So this is that transfer function for the steady-state control error. So now what we can do with this we can take that transfer function and set up the denominator into standard form. So I'm going to do that now. Okay, so it'll be 2 plus k sub d times s plus kp. So that denominator tells us where this function is stable or unstable. We can find the poles from there. But we were given in this problem, conveniently enough, our zeta and our time constant. And zeta is telling us that this problem, I want to say, is critically damped. But let's see if I'm right. Because we know that this guy equals 1, this guy equals, say, 2 seconds. Okay. So knowing these, we can figure out some stuff. We can figure out that this is 1 over sigma. So that means sigma is just 0.5. So it is 0.5. So let's take a look. Yeah, that's right. So 0.5 on the left hand plane, meaning that this is a stable system. So if it's a stable system, we can figure out stuff from that. Yeah. So let's recall some expressions that we know. Better yet, yeah, I'll recall this expression, why not? So in this case, it's 2 plus k sub d, 2 kp times 10. Okay, not that helpful right now. So let's try another one. Let's recall that tau is equal to 1 all over zeta omega n, which in that case, 1 all over zeta square root k over m. So knowing that, we're now going to plug in the 1 for zeta, and we're going to plug in what we know for k and m. So we have 2 equal 1, 1, kp all over 10. So we can figure out what kp is. So it's 2 equal 1 all over square root case of p all over square root of 10. We can flip that over. It'll be 2 equals square root 10 all over square root kp. I can square both sides, which will give us 4 10 over kp. Do it again, we'll have 4 kp equal 10, and then we'll have 10 divided by 4. So what is 10 divided by 4? 2.5. So this turns into kp equal 10 over 4, or kp equaling 2.5. So now, since we know kp, we can find kd. So kd now, I don't know what room, we're going to recall that this here is going to be c all over 2 square root km, and that was going to be 2 plus k sub b, 2 kp, but that's 2.5. So 2.5 times 10 is 25. 25, but square root of 25 is just 5. So it's going to be 1 equal 2 plus kp all over 10. 10 equals 2 plus kp, and kp is now equal to 8. Cool. We have kp value and our kd value. Okay. So yeah, this one's done. Steady state command error. Okay, let's find what that is. We're going to need the closed loop transfer function. I believe that we found. It's right there. That's what we need, along with the error function. So recalling the transfer function is to be E of S equals theta sub R of S minus theta of S. All right, we know that what we can do with this to make it match is have E of S theta sub R of S minus theta of S multiplied by theta of R of S all over theta of R of S. We notice that certain things match, right? Because we want this to match. We want this to match. Well, they do. So, seeing that they match, I can write this again as E of S equals theta of R of S minus H sub C of S theta of R of S. E of S now will equal, I can pull the the theta sub R of S out, and we're left with 1 minus H sub C of S. Okay. Now I'm going to plug in what everything actually is. We're assuming that the inputs are initiated by step responses. So I can write 1 of S. And we're 1 minus Kp plus Kd S 10S squared plus 2S plus Kp plus K sub D of S. So we're going to have 10S squared plus 2S plus Kp minus Kp of S jumping the gun there, plus Kd of S minus Kp minus Kd of S all over 10S squared plus 2S plus Kp plus K sub D of S. And then we have that. Notice that these cancel out. They go away. All that goes away. And then we're left with capital E of S 1 over S 10S squared plus 2S all over 10S squared plus 2S plus Kp plus Kd of S. Not too shabby. So now, as it approaches infinity, will equal the limit as S approaches 0 times S times that whole expression above So here is this. These are gone. And if I got to plug in the values that I do know. So plug in the values that I do know. This kind of transforms into a limit as S approaches 0. S squared plus 2S 10S squared plus, so KD was 8, so that's plus 10S plus 2.5. Let me check something real quick. I call them both KP. That doesn't make much sense, does it? So this is KD. It's a mistake on my part. I'm tired. Okay. So what I wrote, though, is correct. That is correct. So you plug in 0 for everything. And if you plug in 0, these go away. And you're left with you're left with 0. So E is 0. And now for the other one, the next part. So I'll move this whole thing. Move this guy out the way. So for this case, for part C, we're considering the disturbance. So considering the disturbance, this guy becomes 0. And what happens is we'll have this. What we have for this portion. We separate and try to get the disturbance transfer function that we're looking for that particular gain. So theta of s, t sub d of s, negative 1 over s squared plus 2s minus d plus kd of s. Okay, 10s squared plus 2s. We obviously know we can multiply the top and bottom by 10 squared plus 2s, 10s squared plus 2s. We go away, and we're left with theta of s, t sub d of s equal negative 1 10s squared plus 2s. plus Kp plus Kd of S. That's what we're looking for now. We're copying. So since we have that, now we need to recall. And let me just go ahead and make that yellow. And you notice there's really hardly any difference between these transfer functions, by the way. Since you see it above us, there's, really hardly any difference besides the numerator. Numerator are totally different, and that's why you have to kind of watch out for the math. So, so I'm doing this. Error function theta of R of S minus theta of S. Obviously, you're going to say this guy's 0. I'm just going to jump to the expression we need, which is just going to be A minus H sub D of S theta sub R of S. Cool. So I'm going to grab what we need. All right. There we go. Oh yeah, it's -2. So now we're going to plug in E that approaches infinity, stirred, limit as S approaches 0, S 1 over S 1 over 10S squared plus 2S plus Kp plus Kd of S. You plug in 0, everything zeroes out except Kp. So, oh, and yeses cancel out, by the way. They're gone. It's 1 over Kp. And Kp is 2.5, which will give us 0.4. So this solution as this approaches infinity is 0.4. So that is the last part of this problem. If anyone watched, thank you for sticking to the end of this problem. These problems get kind of in depth and hairy. So, if I exit out, back out of this, it's a lot of work. And this is essentially an infinite page. So probably about 3 or 4 pages worth of work right here. So I'm going to exit out of this and I guess call it a night. I got more studying I got to do, but yeah. Thank you for watching if you watched.